Yogaha Karmasu Kaushalam.
Hello everyone, I am Dr. Aditya Vora from Department of Physics, Gujarat University, Ahmedabad. Today, I am going to talk about the study of various properties of disordered materials by computer simulations. Now, disordered materials have recently made an impact on solid-state physics because of their technical importance. Computer-assisted physics can be considered the third approach besides the experimental and theoretical physics, while numerical simulations is especially useful in the study of various properties such as structural, electrical, vibrational, dynamical, superconducting, magnetic, and thermodynamical properties of non-crystalline materials. And these are the example of non-crystalline materials. For example, the liquid metals, liquid alloys, metallic glasses. It will be discussed in this particular lecture. Very recently, the pseudopotential theory is found successful for studying such properties of non-crystalline materials. Therefore, some application of the pseudopotential theory-based computer simulations of these materials will be discussed in the present talk. My plan of presentation is what is disordered materials, importance of computer-assisted experiments, what is pseudopotential, types of pseudopotential, characterization of the parameters, uses of the pseudopotential, some basics of the density functional theory, what is molecular dynamics, conclusion, and finally, the references. First, I would like to say about some introductory part of the disordered materials. Generally, during the several decades, a considerable theoretical development taken place in the field of this disordered condensed matter physics. In this field, the disorder means it is a periodic random structure. The few examples of this system are the crystals with the impurities, liquid metals, liquid alloys, metallic glasses, amorphous solids, etc. The disordered materials are also known as the non-crystalline materials. So it is a more fascinating name of the disordered materials. On the basis of modern concept, the matter is more conveniently divided into the two states, the condensed state and the gaseous state. Condensed matter physics deals with the study of the physical properties of the matter in this state. So the condensed state is being subdivided into the two parts, solid and the liquid states. So generally in the crystalline materials, whose constituent particles, that is atoms, ions or molecules, are relatively fixed in a position except for the thermal vibrations. While for non-crystalline materials, these are having the liquid type in nature. So the example of non-crystalline materials are the liquid metals, liquid alloys, metallic glasses, and so-called, you can say that, the amorphous materials. So first, I would like to say something about the liquid metals and liquid alloys. The major effects in the solid-state physics have been confined to understand the properties of the crystalline solids. But the research on the non-crystalline solids has become one of the fashionable subjects in the field of solid-state physics. For the several years, partly because of the outstanding progress in the preparation technique of these materials, and partly because of a promising prospects for these materials as a device in the technological aspects. So metals are the most important and earth abundant materials. In the periodic table, we can see that the 91 of overall 118 elements, these are having the metallic form or metallic nature because they generally exhibit the good electrical and thermal conductivity, excellent mechanical properties, and unique chemical properties, etc. so which can be widely used in applications ranging from the conducting wires and thermal conductors, structural frames, and pipes to the coatings, medicine, and catalyst. While alloys are made up of from the two or more than two component, metallic component. For example, if we constructing the alloy LiNa, then it is the combination of the two elements Li and Na. Similarly, you can construct the ternary, quaternary, hexanary alloys. So here, these alloys actually are having dependent on the you can say that the different concentration of the metallic substances. So here the X, Y, Z, these are the concentration. It gives the concentration of the typical metallic elements. This concentration play an important role for constructing the alloy structure. Now, most of the metals are in the field of solid state at room temperature. But if we are considering the liquid metals, so their melting points are either lower than or close to the room temperature, which enable them to remain in the liquid state at room temperature. So this brings them additional advantages in comparison with the other metals. For example, they are the fluid, stretchable, and reformable at the room temperature. Recently, great improvements have been achieved in developing the multifunctional devices by using the liquid metals and their alloys, including the actuators, flexible circuits, biodevices, and self-healing superconductors, etc. So these applications are mainly based on the unique properties of the liquid metals, including the low melting point, flexible type nature, stretchable mechanical properties, excellent electrical and thermal conductivities, and biocompatibility. This slide, you can see that the different applications of the liquid metals according to their properties. Now, another technological important materials in the non-crystalline group is the metallic glasses, or the some fascinating name of this material is the bulk metallic glasses. So this bulk metallic glasses is made up of two or more than two components of the pure metallic elements. The mankind has been manufacturing glassy materials for several thousand years. Compared to that, the scientific study of the amorphous material has a much shorter history. Basically, a material is amorphous when it has no long age order. That is, there is no regularity in the arrangement of its molecular constituents on a scale larger than a few times in the size of this group. So glassy materials can be prepared by a variety of methods. Evaporation of metals in vacuum and condensation of their vapor on a cooled substrate, sputtering by which the atoms are removed from the source under bombardment with the energetic inert gas atoms, chemical or electrolysis deposition, a method in which ions in aqueous solution are deposited onto substrates by the chemical reaction through electrodeposition technique, where the chemical reaction requires the presence of an electrical potential. And lastly is the rapid quenching from the liquid state. So amorphous alloys prepared by the latter method, means rapid quenching method, are the so-called metallic glasses or the glassy materials. In this slide, you can see that the volume temperature relationship between the glassy, liquid, and the crystalline state. So the temperature range, okay, seen here between the Tm and Tk, you can see that the three different states of the non-crystalline materials are seen here. Okay, the Tm is the freezing or the melting temperature, and Tg is the glass transformation temperature. Okay, above the melting temperature, the non-crystalline materials, it is in the liquid form, and below the, after the freezing part, below this freezing or melting temperature, the liquid goes on the supercooled liquid and up to the glass transformation temperature. Then finally, when the temperature reaches at the TG, means glass transition temperature, the non-crystalline materials, particularly liquid, will undergoes into the amorphous state. Okay, so glasses, like ordinary liquids, it possesses the atomic order only over a range of the order of 1 interatomic separation, which are shown here in the two figures. Left-hand side figure gives the regularly repeating structure of the crystals, means crystalline materials, but the right-hand side figure represents the random network of the glass. You can see that the atoms are periodically arrangement in the crystal type nature, but in the non-crystalline materials, it is the non-periodically arrangement. Now, preparation of the metallic glasses. Or you can say that the properties of the metallic glasses. We already discussed the preparation technique, but now we are dealing with the properties of the metallic glasses. So actually, the metallic glasses are having the high strength, but they lighter in weight. They are ductile, malleable, brittle, and opaque. Hardness is very high. The toughness is very high. That is, the fracture resistance is very high. High electrical resistivity, high electricity, high corrosion resistance. They are soft magnetic materials. As a result, easy to magnetization and demagnetization are possible. Narrow hysteresis loop, thus hysteresis energy losses. They have high electrical resistivity, which leads to a low eddy current loss. So in this slide, some applications of the metallic glasses are discussed. Generally, these materials are used as a transformer core materials in high power transformers. Due to its high electrical resistivity and nearly zero temperature coefficient of the resistance, they are used in making of the cryothermometers, magnetoresistance sensors, and computer memory. So as the magnetic properties of them are not affected by irradiation, hence they are used in making the container of the nuclear vessel disposal. These materials are used in preparation of the magnets for fusion reactors and magnets for leviated trend, etc. It can also be used for making the watch cases to replace the Ni atom and another metals which can cause the allergic reaction. They are used in cutting and in surgical instrument. In future, it will be used in the electrical field, can yield stronger, lighter, and more easily molded casting for personal electronics products. Also, they are used in tape recorders as working as a heads in the manufacturing of the springs and standard resistance, etc. So from this different applications of the metallic glass, you can see that how the technological importance of the metallic glasses materials. Now this slide shows some of the important technological applications of the metallic glasses. Now next task is to study about the types of the metallic glasses. Generally, the metallic glasses are having the two types. First one is the metallic glasses, and second one is the metalloid metallic glasses. In metallic glasses, they are formed by combination of the different metals. For example, Ni, Nb, Mg, Zn, Cu, Zr, Hf, V, Ca, Mg, etc. While the metalloid metallic glasses, they are formed by the combination of the metals and the metalloid elements. For example, if we are constructing the glass by using the metals like ApCONi and the metalloid such as the B, Si, C, P, then you can construct the glass by ApB, FENI, FEC, FEP, etc. So these are the metalloid metallic glasses. Now next task is to discuss about the importance of these computer assisted experiments. In physics, as in any other field of this natural science, basically the research has been traditionally carried out in the two ways, through the experiments and the theoretical analysis. For the last few decades, a new trend of computer-assisted physics has been established mainly as a result of the remarkable developments in the computer technology. Today, the approach of the computational physics is even mentioned as the third physics, following to experimental and theoretical physics. So this terminology by no means indicates that the computer-assisted physics ranks third. It simply reflects the fact that this approach comes chronologically after the first two. So as a matter of the fact, this new branch of research has made a number of impossibilities possible and brought about a series of breakthroughs in the physics. Judging from the extremely rapid progress in the performance of the computers and from the increasing need for the understanding of systems far more complex than the traditional techniques of the natural science have ever handled. So it is expected that the roles played by the computer-assisted sciences will become important in the century to come. Generally, the computer simulations consist of the two steps. The first is the construction of the physical system according to some given rules of the physics, and the second one is the measurement or the calculation, and finally the analysis of the various physical properties of that system. In the study of the condensed matter, the first step requires the realization of the system, which is composed of many particles that mutually interact by means of the theoretically determined potentials. And then the time dependent of the physical system thus constructed is generally solved by either the stochastic way or the deterministic way. As for the stoichiometric procedures, the Metropolis algorithm, which has been proven to lead a system to its thermal equilibrium, it is widely accepted and forms the main part of the Monte Carlo simulations. On the other hand, the deterministic procedures assume that the particles obey classical mechanics so that the coupled Newtonian equations describe what happens in the condensed matter. So this technique is referred to as the molecular dynamic simulation. The reason for this success is that the computer simulations have much wider scope than the conventional experimental and theoretical physics. The advantage of this particular simulations over the experimental physics are clearly manifested in the description of the how they overcome the difficulties produced of the experiments. First one is the computer simulations can deal with the system that do not exist in the reality and are therefore experimentally inaccessible. For example, it is possible for the sake of revealing fundamental rules of the nature to construct the system composed of the particles interacting by means of the imaginary model potentials. Second one, the wide variety of the physical properties are measured in computer simulations, whereas only a limited class of the physical properties it can be observed in the laboratories. For example, the full information about the positions and the velocities of all the particles in a simulation systems is available, from which any desired microscopic physical quantities can be derived. Third one is the some extreme limits cannot be realized even by the state-of-art apparatus. So they are produced in the computers. So example including exceedingly the high pressures and extraordinary rapid conch rates, etc. So you can say that the extreme limits cannot be fixed by these computer simulation methods. Although it is difficult to establish experimentally unique relationship between the input and output data, which causes and the effect between them, it can be verified without any ambiguity in the computer simulations because input conditions are controlled by the computers. So the methods of the computer simulations, it can be compared with those of the theoretical physics as follows. First, to make the real physical systems tractable by theories, it is always necessary to extract the essential aspects and construct the simple models. Very often, rigorous solutions are achieved only for oversimplified models, and accordingly, the physical relevance of the solutions is questionable. Now, the next one is what is pseudopotential. The pseudopotential formalism is one of the simplest and handy tools in the investigation of the various physical, chemical, electrical, mechanical, and magnetic properties of the crystalline and non-crystalline materials, including the metals, alloys, metallic glasses, nanoparticle systems, etc. So the term pseudopotential was first coined by the well-known physicist Fermi in connection with the problem of the low-energy nucleon-nucleon scattering with the framework of the first-order perturbation theory. This slide gives the timeline picture of the pseudopotential. Fermi was given the first idea of the pseudopotential in 1935. Then after, the Herring gives the OPW method, orthogonalized plane wave method, in 1940, and the first pseudopotential formulation in the equation type nature is given by the Phillips and Kleinman between the 1940 to 1960. Then after, the density functional theory given by Hohenberg and Cohen is established between the 1960 to 1965. Then the well-known Scroft empty core pseudopotential is developed by the Scroft between 1965 to 1970. Then 1970, the empirical pseudopotential is developed between 1970 and 1975. The empirical norm-conserving pseudopotential was given by Top and Hopfield between 1975 and 1980. Ab initio norm-conserving pseudopotential was given by Heman, Coulter, and the Siang. And finally, the separable form of this pseudopotential in the ab initio form and the Carpellino pseudopotential was established between 1980 and 1985. And at the 1990, a different approach, for example, the ultrasoft pseudopotential given by this Vanderbilt, RRKJ pseudopotential established, and after the 1990, the Truller-Martin pseudopotential is generated. So you can see that how the pseudopotential is developed in the different eras of the different timeline sector. Generally, the pseudopotential concept comes from when the electrons experience a Coulomb potential due to the nuclei, then it gives the simplest form. You can write down this nature like following equation: V is equal to minus Z by R. But this leads to the computational problems. When we are putting the values R is equal to 0, then you cannot get the correct answer because the terms gives the value infinite. So this terms leads to a computational problems, especially when we are using the concept of the plane wave basis set. So basically, to minimize the problem, to reduce the problem, there are many interacting electrons are treated to solve numerically by using the various methods given by Schrodinger equations or the Dirac equations, Hartley-Fock equations, Cohen-Sum equation, etc. So you can deal with these three equations to study the Coulomb potential of that particular our materials in the computational way. So this slide gives the some of the glimpse of the how the pseudopotential is proposed in the real space and the reciprocal space. Generally, this pseudopotential, it is our own pseudopotential, which is constructed by ourselves. Since core electrons is situated at energetically very deeper states, they are inert chemically. So the molecules and the solids, they do not change so largely. There is a way of constructing an effective potential which consisting of the nucleus potential and the Coulomb potential given by the core electron states by using the OPW method. In the effective potential is much shallower than that of the true nucleus potential. So it is expected that the calculation will become quite easier. Generally, the force acting between the atoms in a solids are the electrostatic in nature, and that depend upon the outer electrons in the atoms are the dispersed in particular space. So the pseudopotential is one of the procedure to deal with the Schrodinger equation and contains the vital features of the behavior of the electrons in metallic system. Here you can see the figures, particularly in the real potential as well as the pseudopotential wave function. So the comparison of the wave function in the Coulomb potential of the nucleus, it is given by the blue line, and the one of the pseudopotential is represented by the solid red line. So the real and the pseudo wave function and the potential related to these two wave function match above a certain cutoff radius RC. So beyond some reasonably small core radius RC, most of the ion potential is local, specifically in Coulombic nature. So inside the core region, in addition to the Coulomb potential, is the net ion charge JD. So the bare ion potential contains a repulsive term arising from the fact that the conduction electrons are excluded from the core region by means of the Pauli's exclusion principle. So the repulsive term tends to cancel most of the attractive Coulomb potential in the same region. So thus the pseudopotential is seen weaker inside the core region and pure Coulombic outside the core region. Usefulness of pseudopotential. So generally, this method is simple conceptually and computationally. The result properly generated by using this method are were comparable with those obtained from the first principle electronic state calculation. Such a method is not useful only for the static properties, but it is useful for the dynamical properties too, and the electronic properties also. Almost all types of the imperfection in the crystal structure can be studied by using this method. Within the certain approximation, it fairly reliable analytical forms of interatomic interaction it can be obtained by using this method. It directly provides the information of the 3-body and 4-body forces in the metals via perturbation expansion. The use of such method readily can be extended to the liquid metals, alloys, and metallic glasses. Also, such a method allows an easy way to perform the comprehensive study of almost all the properties of the condensed matter. So the pseudopotential term can be conveniently defined as the fictitious or the artificial but physically justifiable weak and effective potential seen by an electrons in the vicinity of the ions and the clouds of the surrounding electrons. Or you can say that the pseudopotential, it is nothing but it is the net effective potential in the neighborhood of the ion core seen by electrons. So the pseudopotential matrix element is represented by in the following form. Here the SQ terms is nothing but it is the structure factor, and it carries out all the information regarding the structure of the material, and it depends only upon the ionic position of the material. Finally, when we are putting the values of this SQ in this first equation, matrix element of the pseudopotential, then you can find out the pseudopotential equation like that. And this pseudopotential equation is represented in terms of the form factor. So this form factor depends only upon the individual ion potential and independent of the ionic position. So it is known as the pseudopotential form factor. Here the symbol omega 0 is nothing but it is the atomic volume of the material. So if the form factor W depends on the only single wave vector Q, so it is called the local pseudopotential. While if the form factor W depends upon the two wave vector Q and K, then it is called the non-local pseudopotential. A non-local pseudopotential is extremely inconvenient to work with, because for any given pair of the Q and K, the function that must be calculated for each of the wave vector Q and K are rather complicated. Therefore, most of the people prefer to work with a local pseudopotential. So we have an interesting freedom with the local pseudopotential is that its form is not a unique one. Due to the electrostatic potential between the ions and the electrons get attracted towards the ions. So this surrounding electrons shield the potential of the ions, and therefore the rest of the electrons will have to face the two potentials due to the positive ions, and second one is the screening electrons. So these electrons again shield the ion potential, and the process goes on infinite times. So you can see that the pseudopotential goes on weaker and weaker. So at each successive screening, the net potential becomes the weaker one. Finally, after successive screening process, the screen form factor is written as the following equation: WQ is equal to WBQ by epsilon Q, where epsilon Q is nothing but it is having some notation, and this epsilon Q is represented by modified Hartree dielectric function. Here epsilon H is nothing but it is the Hartree dielectric function, and FQ it is called the local field correction function, and it incorporates the exchange and correlation effects in the screening function. Various forms of FQs are available in the literature, so you can use or you can put the different FQs in this equation, and you can get the different results according to the different type of FQs. Now next task is to study about the different types of pseudopotentials. Generally, the pseudopotential are having the following different types. Local pseudopotential. This local pseudopotential are again subdivided into the two parts: single parametric pseudopotential and the multiparametric pseudopotential. Then non-local pseudopotential, norm-conserving pseudopotential given by the Truller and Martins, ab initio pseudopotential, empirical pseudopotential, ultrasoft pseudopotential given by Vanderbilt, etc. Now, from the literature survey, there are 23 single parametric local pseudopotential found, in which few are directly proposed in the reciprocal space, while the few are in the real space, while 54 multiparametric pseudopotential are proposed in the literature, and the 5 non-local pseudopotential are available in the literature. So most of the pseudopotential are having dependency of only a single parameter, that is the pseudocore radius, or you can say that the model potential parameter RC, either or with the another parameters. If we are having the single parametric local pseudopotential, then it is only depending upon the single parameter RC. But if we are using the multi-parametric potential, then this multi-parametric pseudopotential are having the two or more than two parameters. One parameter is associated with the potential parameter RC. If we are studying the pseudopotential part in the search engine, then you can find out the more than 200 research papers are found based on the Ashcroft's empty core local pseudopotential in the literature. It is a simpler one, and the most of the citations are given by the different researcher to this potential. After the development of the pseudopotential, the next task is to characterize to its parameters. So there are the several methods are used to characterizing the model potential parameters, such as the Q0 method, zero pressure method, universal method, etc. So first we discuss about the Q0 method. The parameter of the potential is determined from the Q is equal to Q0 value of the potential. So it is one of the most popular method. Here the Q0 is the value of the wave vector Q from where the pseudopotential form factor passes through the first zero. So the requirement to determine the parameter RC of the potential by using the Q0 value, which leads to the following equation. WQ is equal to Q0 is equal to 0. It gives the value of Q0. Second method is the zero pressure method. So the determination of the potential parameter using this method is employed successfully to investigate many physical properties of the materials. Because this method is free from any fitting with the experimental values. At low temperature, the pressure P is obtained from the first derivative of the total crystal energy with respect to the atomic volume, omega 0. So according to the zero pressure condition at low temperature, the system remains in minimum total energy state at the constant volume, and the pressure exerted on the system becomes 0. So mathematically this expressed as P is equal to minus dE by d omega 0 at R is equal to RC. This is equal to 0. Now next one is the universal method. So generally the peoples will have the flexibilities to use any of the metals. So universal method, actually it is given by the various researchers for generating the pseudopotential parameters. First method, actually here the model potential is determined from the first dip minima of the pair potential. It is called the zero force at the first nearest neighbor distance method, N0 method. This technique is also used frequently to determine the parameter of the potential, especially when the static and vibrational properties are to be investigated. Second universal method is given by the Hein and Wire. It gives the simplest relationship. RC is equal to 0.51 Ra Z raised to 1/3, where Ra is nothing but is the atomic radiation, Z is the valence. So you can find out the values of RC with respect to the two parameters Ra and Z. So this method is successfully applicable for the elements having the Z is equal to 1 and Z is equal to 8. Again, the different researchers, particularly this Jani and Patel, have proposed the universal method in terms of the quantum number dependency. So the potential parameter is computed by using the quantum numbers by applying this particular equation. Beta is equal to RC into L plus S Z raised to 1, or Z raised to L, sorry, all raised to 1/3. Here, Z1 is the effective nuclear charge seen by electron near to the ions, which does not possess the d electrons in the last cell. while it may be considered the valence of the element if d electrons are available in the last cell. Fourth method is proposed by Cohen and Hahn. Here the quantum number L in the pseudopotential calculation from the repulsive centrifugal barrier part L plus 1 by R square, which occurs in the radial part of the Schrodinger equation. Again, the different researchers have given the different universal methods for find out the model potential parameters. Now, uses of the pseudopotential. Using the pseudopotential theory, many properties of the solids, liquids, and the amorphous material are successfully studied, such as the electrical transport properties, magnetic properties, static and vibrational properties, dynamical properties, structural properties, phase diagram calculation, Fermi surface distortion calculation, band structure calculation, thermodynamical properties, superconducting properties, etc. So first we discuss about the electrical transport properties. So electrical transport properties of the non-crystalline materials are computed by using the well-known Zeeman's theory. So electrical resistivity is computed by using this equation, rho is equal to this equation. Thermoelectric power is measured by using the second equation, and the thermal conductivity is computed by using third equations. So you can apply these three equations and find out the electrical properties for any of the metallic complexes. Here are some of the results of the electrical properties of the liquid alkali metals. You can see that from this slide, the computationally generated result are found the much qualitative agreement with the available experimental data. In these slides, you can see that the electrical properties of the bulk metallic glasses or the bulk amorphous materials, the sum of the materials, the experimental result of the sum of the materials are not available for comparison, but you can get the electrical properties of all the materials by applying the pseudopotential theory. Okay, these are the graphical representation of the electrical properties of the binary alloys. So first picture represents the resistivity. So this resistivity again vary between the two concentration of the material 0 to 1. Similarly, according to the resistive nature, the thermoelectric power and thermal conductivity are generated. Again, this is the resistivity of the amorphous alloys CuSN. In the left hand side, you can see that the picture of the structure factor of this CuSN alloys. So black one represent the structure factor of the Cu element. Then you can find out the value of the total structure factor by the dotted line represented by the dotted red line. So the total structure factor gives the total structure factor of the particular liquid materials, and some of the partial structure factors related to the different components of the metals. Again, this is the thermoelectric power and thermal conductivity of the CuSN materials. Now, second one is the magnetic properties. In magnetic properties, we study the two different magnetic properties, magnetic susceptibility and the night shifts, by using these two equations for the measurement of magnetic properties for the different metallic complexes. Here you can see that some of the results related to the magnetic properties of the liquid alkali metals. Electrical susceptibility results are also seen here in the slides of the liquid metals. Again, here you can see that the theoretically generated result and the experimental result both are found in comparative way. Static and vibrational properties. Here we calculate the phonon dispersion curves, static properties, vibrational properties, phonon density of states, etc. So this slide gives the phonon dispersion curves of the liquid Li element. Here you can see that the two branches are same, longitudinal branches and the transverse branches. Again, this is the phonon dispersion curves of the liquid alkali yellowish for the different proportion or the different concentration of the metallic components. These are the phonon dispersion curves of the bulk metallic glasses. This slide shows the electron dispersion curves of the liquid metals. Again, this is the electron dispersion curves of this CuGa alloys. Here you can see that the depth of this particular electron dispersion curves is found at the peak of the structure factor. Again, after computing the electron dispersion curves, you can find out the Fermi energy of the liquid metals. So compare this Fermi energy with the pre-electronic value of the Fermi energy. So you can find out the qualitative agreement between them. This is the value of the density of states of the liquid metals. In dynamical properties, we compute the velocity autocorrelation function, power spectrum, diffusion coefficient, mean square displacement, etc. Again, this is the results of the mean square displacement, or you can say that this velocity autocorrelation function of the liquid metals. This is the power spectrum of the liquid metals. Again, velocity autocorrelation function of the liquid alloys. In thermodynamical properties, we calculate the internal energy, entropy, Helmholtz free energy, entropy of mixing, heat of mixing, etc. for any of the metallic complexes. So the total energy of each of the elements are seen here. So it is compared with the experimental one. This is the result of the total entropy. Again, in these slides, you can see that the various contribution to the entropy for the NAK binary alloys, as well as the heat of mixing of this particular binary alloys. Excess entropy is also computed for this binary alloys using the pseudopotential theory. Now the next one is the superconducting state parameters. Here we study the electron phonon coupling strength, Coulomb potential, Coulomb pseudopotential, transition temperature, isotope effect, exponent, effective interaction strength, etc. So these are some of the result of the superconducting state parameters of the different elements in forms of the metal alloys as well as the bulk metallic glasses. You can see that all the parameters are found the comparable with the available experimental data. These are again the graphical representation of all the superconducting state parameters at the metallic glasses, COZR metallic glasses. This also gives the another parameter of the COZR bulk metallic glasses. So the pseudopotential, when we are considering this method, particularly in the computational, using in a computational task. So this theory is found computationally supportive formulation, which is suitable for any of the compilers. For example, Fortran, C, C++, Mathematica, MATLAB, etc. Now, I want to discuss about the basics of the DFT. So density functional theory is one of the most popular and successful quantum mechanical approaches to the matter. It owes the versatility due to the generally of its fundamental concepts and the flexibility one has in implementing them. So furthermore, one can say that it is computationally simple nowadays. So for this reason, it has become a common tool in the first principle calculation, which aimed at describing or even predicting the properties of the molecular and the condensed matter systems. The DFT problem is the non-trivial one. So the DFT is based on the famous theorem given by the Hohenberg and Cohen, who demonstrated that the total energy of a many electronic system in an external potential is a unique functional to the electron density, and that such a functional has its minimum at the ground state density. So expressing the electron density as a sum over one electron densities and using the one electron wave function as the variational parameter, which leads to the Cohen sum one electron equations. Here, the exchange and correlation potential has been expressed as the functional derivative of the exchange correlation energy, as the core element is strictly related to the Cohen sum theorem and their equations. So these are the some result generated by using the density functional theory. First figure shows the electronic band structure of the alpha uranium, and second figure represent the Fermi surface of the alpha uranium. Again, this slide shows the total density of states, integrated density of states, and partial density of states of the alpha uranium, which are computed by applying the density functional theory. Now, the next computationally aspects is the molecular dynamics. So, molecular dynamics, it is the solution of the classical equation of the motion for atoms and the molecules to obtain the time evolution of the system. So, applied to many particle system, a general analytical solution is not possible. So, must restore to the numerical methods and the computers. There are the two ways for studying the systems. If we are applying the classical mechanics only, then fully fledged the many particle time dependent quantum method not yet available. And second one is the Maxwell-Boltzmann averaging process for thermodynamical properties. Here one can restrict our problem by taking the time averaging. So these are the some key stages in the MD simulation. You can see that the different steps of the MD simulation: initialization, forces, motion, properties, and finally the summarize. So first you set up the initial system, then calculate the atomic forces, then calculate the atomic motion, then calculate the physical properties. Again repeat, means looping this process up to till the system does not achieve their goal, and finally they produce the final summary of our structure. So these are the different steps or different stages of the MD simulation. Now conclusion part. So in this particular talk, I would like to say something about the different computational aspects of how the different type of theoretical methods are applicable for studying the different properties of the materials. Nowadays, the density functional theory is most popular computational tool for studying the various properties of the solids. So many computationally packages available freely in the search engine. For example, WASP, Win2K, Ebinit, Quantum Espresso, etc. So based on the DFT formulations are available for Linux and Windows-based environment. But due to the fact that the conventional pseudopotential method are found most popular and suitable one than the DFT, because the formulation of the DFT or computation of the DFT is taking more time for the computational part. But when we are using the pseudopotential based computation, then you can get the result in a shorter time. So the conventional pseudopotential method are found most popular because of the wide applicability in the solids, liquids, and the amorphous solids, computationally handy and flexible method, easiest formulation and suitable for all environment, etc. So the pseudopotential method is applicable to all of the state of the materials. Means you can apply this material to the solids, means the crystalline state, as well as the non-crystalline state, particularly in liquid and amorphous material. But DFT having some of the limitation, it is only applicable to the crystalline materials. So the scope of the computer simulation is not limited to numerical or the quantitative achievement. Rather than it is in the qualitative aspects that the method of the computer-assisted physics reveal their greater power, partly because of their high ability and partly because of their rapid progress in the computation. So the importance of this method will increase in the future. However, it must always become in mind that the physics is most essential in the performance of the computer-assisted physics, just as in the case of experimental and the theoretical physics. So these are some of the references according to which this presentation are designed. Okay, thank you and namaste to all.